All right, we'll go ahead and begin. So, I know you've been up in the middle of the night trying to think about terpenes and their crazy structures. You've been waiting for us to get back together again today so we can identify structures in these things. So, as I recall, I last drew you a horrible structure. 5-membered rings fused together with other things. Ooh, and this one's terrible. Okay, so this is called cedral, and it unsurprisingly is from cedar. I'll tell you, well, if you count the number of carbons there, there's 15. So this is a sesquiterpene and has 3 isoprene units. Remember that when we're looking for isoprene units, we're looking for the framework of sigma bonds that follows this pattern. And the way I've chosen to number these things is 1, 2, 3, 4, and 5. And because all of these come from similar linear precursors, which we drew last time. In this case, it's a sesquiterpene, so there would be 3 isoprene units in this starting material. And we can highlight them here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's see, what other color can we use? 1, 2, 3, 4, 5. Okay, so all of the carbons here have to come from this linear precursor. We're going to talk about how mechanistically that might happen. But what we want to do is identify the different isoprene units within this structure, because that will give us an idea of the bonds we have to make. Okay, and as we talked about last time, remember that the bonds present in the linear precursor in between isoprene units are the sigma bonds between carbons 5 and 1. So those are bonds that we're not going to have to make as we go from this linear precursor to this product. But notice that in the linear precursor we have what I've called the dimethyl tail. That means at some point in this molecule, we're going to have a tertiary carbon that's bonded to 2 other carbons, and those carbons will either be methyl groups or some version of a methyl group. Now, as we look for isoprene units, we're ignoring double bonds, and we're also going to be ignoring oxygens or other heteroatoms. So if I were looking for a dimethyl tail in a molecule that had something like this, I think maybe we did this last time, and that's limonene. This is the dimethyl tail part. I'm ignoring the double bond. Okay? Anyway, so let's go through and see what we can find. First, the branching methyl groups. Remember, those are always carbon 3. So I've got one here, got one here, and then I've got 2 methyl groups there. So that ought to be my dimethyl tail, right? Okay. The carbons that are bonded to the branching methyl groups are always carbon 2. And then if what I've identified here is my dimethyl tail, the other methyl group can be 1. You see that? Question so far about identifying stuff? Okay, so once we've identified those features, we need to figure out where carbons 4 and 5 are. But the thing that's going to help us distinguish where they should be is going to be that carbon 5 of one isoprene unit is always going to be bonded to carbon 1 of another. So what that means is if we get to carbon 5 and it doesn't make sense, the next carbon could be carbon 1 of the next isoprene unit, we've done it incorrectly. Okay, so let's start with the dimethyl tail. 1, 2, 3. Could this be 4? Why not? Because you can't connect to a carbon 1. If this is 4, well, whoops, maybe. I don't know. 1, 2, 3, 4. If this is 5, then could this be 1? Yeah, okay. But this, if this is 4, this can't be 5, clearly, right? Because that's a carbon 2. One of the things your text points out, if you'll read the section on terpenes, it's quite good. There are often multiple ways to identify isoprene units, and as long as your way makes sense, it is right. And again, I know you're not comfortable with that ambiguity because it sounds like I'm saying, well, if your answer's right, it's right. So what do you want from me, right? Okay, so let's choose. Knowing that at this point we could call either of those carbons carbon 4, though if we did that, the chain would have to curve around this way. Let's just choose one, and then we can go back and see if the other works. Okay, 1, 2, 3, 4, and then which way should I go here? Left, right? Because if I go here, that would have needed to be carbon 1. So 5, and then 1. Does that work? Does that make sense so far? Okay, so that's going to be one of those bonds from the first isoprene unit to the second one. So what we're saying here is that that is one of our isoprene units, and it's the pink one, starting with the dimethyl tail. Okay, then we go 1, 2, 3. There's really no other choice. This has to be 4. And then which way should we go? Seems like we could sort of go either way, right? If this were 5, could this be carbon 1? That works out well. If this were 5, could that be carbon 1? Also works out. So again, you hate the ambiguity, but there are a couple of different ways that we could go through this. Let's just, for the moment, oops, I didn't need to erase all of that. Say 1, 2, 3, 4, 5, and then 1, and that'll be another bond. 1, 2, 3, 4, and 5. Okay, so we've identified now the bonds that were present in the starting material. And now there are going to be other connections, which we can highlight in another color, connections that are new to this product. For example, the bond between 4 and 4, that's something we were going to have to make. The bond between 4 and 2 this way, that's another thing we were going to have to make. And the bond between 4 and 5 this way. And then highlighting our isoprene units. All right, so that's one way to divide it up. Pink isoprene unit, orange, and then green. And in red are the bonds that were present in the linear precursor, and highlighted in that weird color of blue/gray are the new bonds that were not in the linear precursor. Sure, yeah, and because we've been ignoring the OH group, yeah, we could, if you want to highlight that as something that we're going to have to put in there later, sure. Yeah. Okay, would it be useful for us to work through some of the alternatives. Go ahead.
So with the 5-to-1 rule, is it just sort of like n minus 1 however many units, there has to be that many 5-to-1 connections?
Sure. The rule is however many isoprene units there need to be. If the number of isoprene units is n, then there will be n minus 1 connections between 5 and 1. Yeah. Okay, do you want to go through that and try to assign them in a different way and see how your answer is still right? No, please, no. Okay. That's fine, we don't have to. All right, so now I want to talk about mechanism. And the precursors to all of these starting materials are two different isoprene units. The first is dimethyl allyl pyrophosphate. Your book will call it diphosphate. I'll call it pyrophosphate because that's what you call a group with the phosphoanhydride linkage between the two. Either terminology is okay. I'm choosing the pyrophosphate terminology because I think in future biochem textbooks they're going to abbreviate that pyrophosphate group like this. And so if you don't know that it's pyrophosphate, you may wonder where that comes from. So this is one of our starting materials, and then the other is this. And that's isopentenyl pyrophosphate. And again, the pyrophosphate group is just a good leaving group. I don't particularly care that you know the names of these things, but you likely will encounter them again in biochemistry, so I want you to have at least heard them. Okay, so we're going to put our 351 hats on for a minute and think about leaving groups. Pyrophosphate's a good leaving group. It's on a primary carbon, but it's not just any primary carbon, it's an allyl carbon, which means that if the leaving group leaves, you've got a resonance stabilized carbocation. So you might expect, among the mechanistic steps that could occur, you might expect to see a leaving group leaves sort of SN1 type step. So that would involve, and I will abbreviate the pyrophosphate group sometimes like this, and that's fine. You can show the leaving group leaving to give a resonance stabilized carbocationic intermediate. Okay, so that's going to be a common thing that can happen in the chemistry of these starting materials. Now, when the leaving group leaves, this generates an electrophile, right? And this intermediate you would expect would be electron poor on that primary carbon and on the tertiary carbon. Remembering that resonance tells you the positive charge is in both places. Okay, the next step can be nucleophile attacks. And this could be any number of nucleophiles, but we're going to focus on using the pi electrons from isopentenyl pyrophosphate as the nucleophile. So a carbon-carbon pi bond is going to attack the electrophile, attack the carbocation. And in general, it's going to attack at the primary carbon. So let me show you how to draw that. Now, sometimes I find that students are uncomfortable with this because you've been taught that tertiary carbocations are more stable than primary carbocations, so wouldn't it be better to have the positive charge here? And I'm telling you that actually you cannot think of these two as different carbocations. They're the same resonance structure. And there's LUMO, or positive charge, on both the primary and the tertiary carbon. And then I suppose you could make an argument that sterics make it easier for this pi bond to attack the primary carbon, and I think that makes sense. But then you could also argue that, and this is sort of the hand-wavy cop-out option, that the enzyme makes it happen that way. But in any case, what we observe for the most part is the pi electrons attack the primary carbon. Now, let's think about what that does. We make a new bond between carbon 5 of one isoprene unit and carbon 1 of another. Well, actually, no, we need to discuss that. The pi bond is shared between carbons 1 and 2. So when we make a new bond, we could make it between carbon 5 and 1 or between carbon 5 and 2. As you saw, and this is also a 351 reaction. Do you remember when we were doing hydration of alkenes and we protonated the double bond, but we chose to do so and make the new carbon-hydrogen bond with the less substituted carbon so that the more substituted carbon could have the positive charge? Does that sound vaguely familiar? And that was what they called the Markov-Nikov rule. Same thing here. We're going to make the bond preferentially with the less substituted carbon 1 so that the positive charge can be on the more substituted carbon where it's more stable. Why do we care about the substitution of this carbon? Well, because this is not a resonance stabilized carbocation. It's just a regular old everyday carbocation. Okay, questions about that step? You've seen alkenes attack electrophiles before. You've seen carbocations be attacked by nucleophiles before. What you may not have seen is an alkene acting as a nucleophile to attack a carbocation. So, but you need really stretch your mind to see how this is not really new. It's the same kind of reactivity you've seen before, just the players are different. Okay, what else? Questions? No? Okay. Yeah?
I think this happens most of the time.
Can I think of any examples where the alkene attacks the tertiary carbon? No. Not in generating the linear precursor. Okay? So a final step that we will often see in terpene chemistry is elimination of a beta proton to give an alkene. So we'll take this carbocation, and this is sort of an E1 type reaction. You learned in 351 that protons that are adjacent to a positive charge are acidic. And there are a lot of reasons for that. We won't go into it, but you were told that if you can identify protons that are adjacent to a positive charge, then you can do an elimination reaction where a base removes a proton and the electrons in that carbon-hydrogen bond kick down to form a new pi bond. That's E1 elimination. So what I'm doing now is I'm highlighting all the different beta protons that we have. Okay? So there was a rule for E1 elimination where the alkene that you got from this process, if there was more than one possibility, what's the major product? I'm hearing whispers of the more substituted one. Okay, good. And that's the Zaitsev rule, if you learn the names of dead folks that discovered these things. You don't have to. So if I were going to choose, I would choose pink or purple. I forget that on the screen pink and purple look exactly the same. So let's go. That's a lovely color of blue. Okay. Purple or blue versus orange. We would definitely not choose orange because that would give us a disubstituted alkene, whereas if we choose pink, blue or purple, we get trisubstituted alkenes. All right, so we'll go ahead and cross this one off the list. Now, you wouldn't expect, based on what you learned in 351, it would be difficult to predict regioselectivity here, and you would probably draw both of the alkene products. But I'm going to tell you the enzyme directs the reaction such that purple proton is removed. And the reason for that is that getting rid of that purple proton puts us back in a situation where we have an allyl leaving group. So just thinking in terms of chemical strategy, once we make the double bond there by eliminating the purple proton, now that leaving group is allyl, and this is now poised, if we need to start right back up at the top with leaving group leaving again. So we can actually, by repeating steps 1, 2, and 3, actually go on to make a linear molecule with 3 isoprene units in it. The one with 2 is called geranyl pyrophosphate. And I think if you go to your text, and do one of the practice problems there, you'll see that through the exact same steps, you can convert geranyl pyrophosphate into this molecule with 3 isoprene units, which is called farnesyl pyrophosphate. So this is how we, and it's just simple SN1 and E1 type chemistry. This is how we generate the linear precursor. Go ahead. For these steps, you don't need specific reagents. No, this is enzyme catalyzed. So in general, we're going to use sort of, well, a base to do that. Of course, in these steps, the reagents are just these starting materials. Yeah. So, okay. For the most part, mechanisms in this part of the class are going to be about not predicting what happens, but showing how something happens. For example, if I asked, can you make farnesyl pyrophosphate from, can you show how you make it from these starting materials? Could you draw that mechanism? All right, so that's how we develop the linear precursors. But these same steps allow us to make more complicated connections. So let's do some examples together. Last time we drew limonene. I didn't worry about stereochemistry there. I'm going to show you what the stereochemistry is in limonene. It turns out stereochemistry changes how it smells. There's this enantiomer of limonene, and then it's other. This one is the one that smells like citrus. The other smells a little bit different. kind of cool that your nose can distinguish between enantiomers. And why is that? Because your nose is chiral and it has chiral receptors in it. Okay, so this is limonene, and it's going to come from geranyl pyrophosphate. And I believe last time we already identified the isoprene units in limonene. Here's one, and then here's the other. And that's 1, 2, 3, 4, 5, then 1, 2, 3, 4, and 5. Here is in red the bond that's in the linear precursor. And then in our lovely light blue color is going to be a bond a sigma bond that we're going to need to make between carbon 5 of the orange unit and carbon 4 of the pink unit. So this gives us an idea of what we have to do in this mechanism. Okay, we're not going to worry about making the bond between 5 and 1 because that's already done for us. All right, so how do we do this? Well, first, let's try to, since we've identified this portion as the dimethyl tail, and this portion also as the dimethyl tail, it makes sense to try to redraw the molecule in a way that would arrange things in a similar shape. So here is the pink unit from geranyl pyrophosphate, and then here is the orange unit. Okay, now we've got kind of a problem because at this stage we could have the leaving group leave, and that's fine. It needs to leave for us to do this chemistry, but the resulting carbocation, that resulting positive charge, is not in the right place. If I want to make a bond between 4 and 5, presumably I could use this alkene between 2 and 4 as a nucleophile, and it could attack the positive charge, making a new bond between pink carbon 4 and orange carbon 5. And that would then leave a positive charge on carbon 2. That sounds great. The only problem is this carbon 5 is too far away. If we made the double bond there, you'd be asking for a trans double bond in a 6-membered ring, which can't happen. So what happens here is that this is a resonance stabilized carbocation, so that the positive charge on carbon 1 can also be on carbon 2. It's resonance stabilized though, so there's a barrier to rotation around this bond between orange 2 and orange 4. And so what will happen, and they've demonstrated this biochemically, is you're going to have the pyrophosphate group attack that tertiary carbon. That gets rid of the barrier to rotation around the bond between 2 and 4. And your text will take you through this too. This is a material called neryl pyrophosphate. It's an isomer of geranyl pyrophosphate. Once we no longer have double bond character in this bond between orange 2 and orange 4, it's then easy to rotate around that bond to give us this conformation. And once we're there, the leaving group can leave again. And now we've got everything in the right place. For our reaction to occur. I'm going to draw the resonance structure that puts the positive charge on carbon 5 of the orange isoprene unit. Now that we've done that, and so far what have we done? Well, we have done leaving group leaves to give a carbocation. Nucleophile attacks the carbocation so we can get rid of double bond character and rotate around the bond, then leaving group leaves again. Nothing new here. The challenge is really just drawing the molecule correctly and seeing and having a sense for the strategy. Now pi bond is going to attack the positive charge on carbon 1. That's going to create our 6-membered ring. And it's going to put a positive charge on pink, oops, not that one, on pink carbon 2. So again, 1, 2, 3, 4, 5, bond in from the linear precursor, 1, 2, 3, 4, 5, and oops. And then this is our new bond that we just made. And again, I'll highlight the isoprene units. Okay, questions so far? Yeah.
Can you briefly just go over like why it's too far away?
Okay, so the argument as to why we needed to go through this intermediate here is that if we tried to have the pi electrons attack that carbon, you would be making a ring that looks like this. And if you try to, on paper you're like, okay, whatever. But if you try to make a model of that, try to have a trans double bond in a 6-membered ring, your bonds won't actually fit. They'll pop apart or you'll break them because you can't, that geometry just doesn't work in a 6-membered ring. There's no way to get from this carbon back around to this one with only 2 carbons in between. So it just, it's just too far away. I don't know if that helps a little bit.
Just because it can't rotate.
And so then the other question is, well, why can't, from this resonance structure, why can't we just rotate around 2 and 4 to bring carbon 5 back over here, and then we could do what we need to do? And the answer is that seems to make sense to me, but this is a conjugated system. You've got a resonance stabilized carbocation. If you rotate around this bond, you break that resonance and it becomes just a regular carbocation, and that's higher in energy. So there's even though you can think, oh, well, there's some single bond character, why can't I rotate around there? Doing so breaks the conjugated system, and so there's a barrier to it. And apparently that barrier is high enough that it doesn't happen very well at physiological temperature. So what nature does is it says, okay, fine, let's get rid of the carbocation by having a nucleophile attack. Then we can rotate freely around that sigma bond, and then once we've got it in the right place, the pyrophosphate group can come off, and then we can make a ring with a cis double bond. Okay, what else? Yeah?
Why does it, so starting with the one on the left, why don't you just take off a hydrogen at the very bottom on the right, and then it just kind of goes like, I don't know, the arrow goes in the other direction? I don't know if that question makes sense.
So tell me where to start. Am I starting here, and which hydrogen
Yes,
are you talking
very
about?
Bottom on the right, take a hydrogen off there, and then that little bond jumps up to the
Oh, you want to do it this way?
Uh-huh.
I mean, ultimately, that's sort of what we're going to do, though there's evidence for carbocationic intermediates rather than negatively charged intermediates, in part because we do see rearrangement products. So, yeah, I mean, what you're proposing is why don't we just go straight to limonene by doing some kind of concerted cascade where base removes this proton, then we get a double bond here, then we make a bond there. Oh, and then that kicks off the leaving group. That's all neat and fine, and that actually makes the correct bonds. But there is evidence for this intermediate, and I'll show you what that evidence is in just a little bit. But you're absolutely right that once you get here to this carbocation, the final step to limonene is an E1 type reaction where some base removes this proton and we create a double bond. At that stage, carbons 1 and 3 are identical, so it doesn't matter which one we deprotonate, and that will get us to our limonene product. All right? Yes? Why wouldn't it form the more substituted alkene? That is a great question. And what is the answer to that? I don't know. This is, you're absolutely right that this is an anti-Markovnikov step. And what? I'm going to punt and say, oh, it's just the enzyme, because I don't know. Okay? But there actually are other things. Nature uses this cation as a precursor to lots of other things. So it's fine to recognize that there's other possibilities, because nature actually uses those. Okay? What else? Yeah?
When the nucleophile attacks, after the nuclear is left, it attacks. Is that where the enzyme would form this stereochemistry?
Right. So you're asking about how do we get this stereochemistry, and we do make a stereocenter when we do this attack step. And so, technically, though it is not at all clear from our stick diagrams how that selectivity would happen, presumably the enzyme directs this double bond to attack this carbon from underneath. Yep. Okay, other questions? All right, now get ready for some fun, because there's a lot of other things that can happen using this carbocation as starting material. And that will get us to some of the other terpenes that we mentioned last time. So what if instead of having that elimination reaction happen, notice that we have a proton on adjacent carbon 4. You had forgotten about this, and I had deliberately not talked about this in multiple times this semester when we could do so. But behold, carbocation rearrangement. Grown. This is a 1,2 hydride shift. That's the evidence, by the way, for the carbocationic intermediate. Remember, a positive charge on a carbon, an isolated positive charge, is consistent with an empty p orbital on carbon 2. This carbon-hydrogen bond on carbon 4 can line up with that p orbital and then lean over into it and then make a new bond with carbon 2. So if we did that 1,2 carbocation rearrangement, 1,2 hydride shift, what would that get us? Well, that would give us the hydrogen is there, and then the positive charge is on that carbon. And it's one tertiary carbocation for another. We'd expect that to be an equilibrium step. Okay? But wait, there's more. Make it stop. Please make it stop. Now, you have in the same molecule a positive charge across the ring from this alkene. And the shape of the ring is such that we can do this. So what would that do? That's going to make a new bond between orange carbon 4 and pink carbon 4. And for those of you playing along at home, you will notice that we made a second bond in this ring, which is going to convert this into a bicyclic ring system. So the new bond we just made will be I'm going to label things before we go on. The new bond we just made will be between orange carbon 4 and pink carbon 5. And that will leave a positive charge on that carbon. And then a number of different things can occur, but if you eliminate this proton, you then have the following molecule, which is called alpha-thugene. And if you eliminated this proton instead, it would be beta-thugene. This is one of my favorites to draw because if you sort of squint your eyes and, let's see, I need a different color. If you sort of squint your eyes and look at it sideways or sort of, I don't know, it kind of looks like a duck. So I almost expect it to ask me if I have any grapes. Yeah, thanks. You guys were like, what, 1.5 when that came out? All right. Now, do you remember alpha-pinene, that horrible molecule that looks like this? Remember that? Turns out we're only a couple of steps away from that if we use this carbocation intermediate. Instead of doing the rearranging, if we have the double bond between orange 2 and orange 4, now attack carbon 2, we're going to make a new bond between 4 and 2, and that will leave a positive charge on carbon or orange 2. So again, it can be helpful when drawing these reactions to first make the connections and then make a more reasonable drawing. So I'm going to show the connection we just made between orange 4 and between pink 2. And if you're counting carbons that are bonded to each other, how many atoms would be in that ring? Well, I've got 1, 2, 3, and 4. So that's a 4-membered ring. And I could actually, if I wanted to, redraw this . One, two, three, four, 5. 1, 2, 3, 4, 5. And then to get to pinene, we just remove a proton adjacent to the positive charge, and then that gets us there. Okay, so lots of fun with terpene chemistry using these very simple steps that you learned from 351. Nature is taking a linear precursor and building things of exquisite complexity, like these would be Lego masterpieces. And it's all having to do with alkenes and positive charges. For fun, do I dare? Yes, I dare. I dare greatly. For fun, see if you can draw a mechanism that would form cedrol from this precursor farnesyl pyrophosphate. I'll put it in the notes, but it would be worth trying. Hint, to get the OH group there, you're going to need a positive charge on carbon 2 that water will attack. Other connections you're going to make as alkenes attack carbocations. Good luck, and may the force be with you. I let you out early. I still had like 3 minutes left. It's okay, I've already seen it start.